Morning everyone. So we're going to continue our final review with the organic chapter. This handout I actually give when we cover in grade 11. We do that quick crash course in organic. It'll go over some of the general patterns for organic chemistry, some of the general naming, and introducing some functional groups. Obviously we went a lot further in grade 12, but we'll start off with this handout here as a nice quick summary for organic. So starting off here with organic chemistry is defined as the chemistry of carbon. Turns out a lot of living molecules, sugars, proteins, they're built off of carbon. The nice property for carbon, I believe it's called catenation, is that carbon, first thing, it has 4 valence electrons. We know that it's the unbalanced electrons that actually do the bonding for us here. Because of the catenation property, carbon can actually bond to itself. That's so far just similar to diatomic, but carbon can actually bond to itself multiple times. What ends up happening is carbon ends up creating a carbon backbone structure. We can start introducing later on carbon as rings. We can start introducing carbon as double bonds and triple bonds. There's going to be a lot of variety that we can get. We know that for the complete Lewis structure, all these electrons have to be paired up. Usually the name part comes from just the carbon skeleton. It's implied that whatever is not shown is hydrogen, although in a lot of organic compounds here, they do have some other elements in addition to C, H. They sometimes have the odd oxygen, nitrogens, and sulfurs, and we saw that with some of our functional groups later on. So we're going to start off here with our simplest organic family in trying to organize some of this chemistry, make it sensible for us. We start off with the simplest family called alkanes, and for alkanes, we are just expecting single bonded hydrocarbons. So carbon and hydrogen bonded in just a long chain or in rings, but no double bonds, no triple bonds here. All organic families come with what's called a general formula, and a general formula relates based on the number of carbons that you have. It's going to actually be able to predict for you just based on that carbon how many hydrogens there are, and in this case here it's 2n plus 2. If you remember, this formula here was derived. Basically, I'm assuming every carbon will at least have 2 hydrogen arms, especially if I'm mid-chain. There's 2 carbons that are special, which are the carbons on the ends. These 2 carbons have the extra unpaired electron, so there's going to be 2 extra hydrogens, and that's where that plus 2 comes from. As we step over to alkenes and alkynes, you saw that the general formula actually changed, so be careful, every single family has its own general formula. We do use that term here, hydrocarbon. I already mentioned if it's not shown, it just shows the carbon for the name of it. It's implied that the rest of it, just remember carbon can make the equivalent of 4 bonds. If I see 4 arms of it, I want to just fill out the rest with hydrogen. So say here there's a double bond here, carbon is using 1, 2, 3 of its bonds. I would expect 1 other hydrogen, 1 other hydrogen. Especially for a double bond, we saw that cis-trans sign isomerism. We'll see that a little bit later as well. Not so with the triple bond, because the triple bond, the carbon is using 1, 2, 3, 4 already. The other carbon is using 1, 2, 3, 4. All 4 valence electrons are accounted for. Now, obviously, we can start off with just plain old hydrocarbons. We can get longer chains. They're all London forces. They start off gaseous from C1 to C4. As we get longer and longer, just the sheer number of charges will make us melt higher. So pentane, C5 to C10 or so, we saw were used for a lot of fuels and gasolines because they were easily transported as a liquid. We can actually substitute these alkane molecules here with halogens. So halogens here, we have the name fluoro, chloro, bromo, iodo. Be careful for these ones here. If I sub on a branch, let's say with carbon, I know every carbon is implied to have 3 valence electrons here. That means this carbon group here is actually a methyl. It's going to be a CH3. While if I put on, let's say, a chlorine, first thing, this chlorine here, even though there starts off with a C, this is not carbon, meaning the parent chain here would still be just a carbon chain. But this chloral group here, it does have a full octet, but it actually has 3 lone pairs. It does not have 3 other H's with it. So these halogens here are just mono-substituted, and they don't need to be diatomic because they're stabilized by the parent. So remember, we're going to get into a little bit of the name of it here. We're going to start off with the parent, which is the longest chain. That's going to be the last word in the name. We're going to number the parent so that the numbers are as small as you can get them. In this case here, I would go 1, 2, 3, 4. And then in case I have multiple branches, in this case here, I have a chloro and a methyl branch. I'm going to alphabetize based on the chloro first. So I call this, for example, while I have it here, 1 chloro, 3 methyl. And I just ram that into the last name. In this case here, it's a butane. Numbers and letters have to be separated by a hyphen. If I do have to condense numbers together, numbers and numbers are connected by a comma. Sometimes they put between the branch and the last name a hyphen, but usually they just ram the last branch with the parent name. the parent not only tells me with the prefix how many carbons are inside, the ending of that parent, we're going to call it the suffix, will actually imply to me what family that we're in. There's a couple different ways of showing these organic structures here. So starting off the one side here is the molecular formula. This is back when we did empirical molecular formula stuff here. We just want a counting number of how many C's and how many H's. So let's just do butane unsubstituted here. So butane here would actually be but is 4. So C4H10. That's the molecular formula. We'll notice empirical formula for that guy there, empirically, it would be simplified. It would be C2H5. That compound actually doesn't exist. In this case here with the 2n plus 2, I know this is the molecular formula, happens in this case here to be twice the empirical unit. In that sense there, that's really convenient to find molar mass because it tells you exactly how many C's and H's that you have. We can go fully into the structural form, which means I list to you all the branches, all the attachments, who's attached to who. You have to include all the H's for a full structural formula. So even if I have methyl and ethyl branches, things like that, I do need to show all the H's, but that shows all the detail, who's bonded to whom. The one thing that it doesn't show is the Vesper geometry. If I try to do Vesper around any given carbon center at a time, I notice every carbon is actually a tetrahedral geometry. The bonding of a tetrahedral should actually be 109.5 as opposed to what looks like 90 degrees right now. That's something your skeletal formula does really well here. Skeletal chemistry here, every corner and every ending is implied to be a carbon. So I would just draw that what's in the blue there. But what's implied here is every corner here is actually a carbon. If I have an ending that doesn't have any branch notification to it, I just imply that's a carbon. These ones here are all just single lines, so I expect it to be a single bond. And with the understanding that the molecule has to have a full octet, we actually understand already that there's actually hydrogens attached to each of these ones here. You would not have to include the hydrogens on this butane molecule. So that's sort of the benefits of the structural formula, especially when we got to structural isomers, you saw that was super helpful. Sort of in between here, especially with molecules, it's a little bit too simplistic with just summarizing how many atoms there are. It's a little bit too much detail for structural or skeletal formula. So what they've done is they've done what's called a condensed formula. A condensed formula tries to summarize some things. It condenses these H's because we're just going to imply all the H's will saturate the carbon for us here, and we'll end up with this ch-ch-ch. Okay, we can actually start off with just ch-ch-ch with all the C's together, especially when we had sort of these middle carbons. We know that the middle carbons only have 2 hydrogens because you're already using 2 arms to hold the rest of the chain. Sometimes they will show this part here as CH2 bracket all 2. Just be careful of how many hydrogens each of these substituents have. If I have a CH3, I know that's a methyl group. I know that would have to be a terminal branch, while here if it's a CH2, it must be mid-branch. We did have to start naming these ones here. Make sure you do know these prefixes here. So far we just go 1 through 10. We used to go mono, di, tri, tetra. For 1 to 4, at least the parent name, we're going to actually switch the parent name to methyl, ethyl, propo, and butyl. I say to myself, the acronym is My Elephant Plays Basketball for MEPH, PB here. But somehow just make sure you remember those 4. The rest are the same: pentane, decane, octane. And all we're going to do is, depending on the functional family and the functional group we're in, we're going to change that suffix, we're going to change the ending to represent which homologous series that we're in. That's another name that IB likes you to know here, is make sure you can define for me the characteristics of a homologous series. So a homolog or a homologous series, here are the couple features. In this case here, your successive members, as I slowly get larger, successive members differ by a CH2 unit. Basically, we're slowly extending the chain, getting it longer. Depending on my functional group here, they're going to actually have the same. Members of the homologous series are represented by the same general formula. So far we've seen Cn 2n plus 2 for general formula for an alkane. This would imply to it would have to have the same functional group. That's the only way for me to actually have the same formula relationship as well. Especially as the chain gets longer, we know carbon, hydrogen, although carbon is slightly more electronegative than hydrogen, it's not enough to make any sort of polarity. So we're just going to say they're all going to be nonpolar. They're all going to just do London forces. But as I slowly get heavier, the more charges we have, we're going to show a gradation in physical properties So my melting point is going to gradually drop. So it's going to get harder and harder to melt the heavier it is. We made use of that in the energy option to actually separate crude oil by boiling point. So gradation and physical properties. But long story short, because we had the same general formula, the same functional group, the functionality will depend on reactive parts like double bonds, like halides that can be substituted. They're going to show very similar chemical properties. So make sure you do know the definition of a homologous series here. Basically, you belong to the same family together. So based on that there, we can do some more terminology here. Alkanes are what are called saturated. When something is saturated, something is completely packed. It's holding the maximum number. In this case here, it's holding the maximum number of substituents. Mainly it's hydrogen unless otherwise specified. A single bond here is only a sigma bond. Because a sigma bond is electron density that's between two centers, these ones here freely rotate no problem. So even though I do have that 109.5 bond angle, single bonds can twist no problem. As we step over to alkenes and alkynes as our next families here, alkenes with the double bond, suddenly I have a sigma, one of these is sigma, and one of these is a pi bond. Because the pi bond is actually going to be a sideways overlap, if this one here were to be able to rotate, I'd actually need to break the pi bond. I wouldn't naturally want to do that. So both a double bond and a triple bond, alkene and alkyne, these ones here are we say they're rigid. Basically, whatever orientation you have around these multiple bonds here, they can't change unless you actually chemically break the pi bond and then reattach it together. We can get cyclo of all these compounds here. Careful, cyclo are not structural isomers of the regular parents. So we just did butane earlier. Butane was C4H10. To become a cyclo compound, I had to ditch 2 hydrogens, making me unsaturated. Every time I unsaturated, I lose 2 hydrogens for every ring that I make and every multiple bond. It's possible your compound can actually contain multiple rings together, but for our compounds here, we're always only going to have 1 ring, and basically we reattach the other 2 together. This one here would still be called a butane, but because I've lost those 2 hydrogens, I'm no longer the same chemical formula, the same general numbers as the straight chain alkene. Straight chain, sometimes we use N for it, and for cyclo, we're going to use cyclo as a prefix. Multiple bonds, double bonds, and triple bonds have a rigid structure. That's true for both double bonds and triple bonds, although for a double bond, because the carbons involved in the double bond, they both hold 2 neighbors, it gave rise to some geometric isomerism. This is spatial or 3D sort of geometrism here. And basically we saw the orientation of the similar groups either gave us cis or trans or gave us our E and Z. We'll come back to that shortly. Let's just do a quick naming structure here. So let's go to 1, 2, 3, 4, 5, 6, 7. Usually we do a zigzag just to represent that skeletal formula, that 109.5 geometry. Let's imagine I have this structure here. Just going to plop down a few carbons. I understand that what's not shown here are just the remainder are going to be hydrogens. We're going to find the longest chain first. So in this case here, it was that one that I counted for you here. Because my longest chain has 7, we look at our prefixes. It could be something heptane. Hep means 7. Alkane means a single bonded family. Heptane would have had the rest of the substituents as hydrogen. So sometimes they try to confuse you and they try to put on an H substituent. I would have assumed that there would be H anyways. The parts that aren't circled, I still have to name. So I have a 1 carbon branch that's called a methyl group. Meth for 1, this is an alkyl group, so it's a carbon branch. So we're going to put methyl, this is a methyl here, this one here is a 2 carbon branch, that's an ethyl. Careful for ethyl, they can even write that there, C2H5. It's basically that 2N plus 2, but I would have lost a hydrogen so that I can actually glom onto the parent chain. If I have different branches, I alphabetize them, and I also want to number the parents so that the branches occur at the smallest number possible. If I number it left to right here, my first branch is at 2, 4, and then 5. If I number it the other way, bottom up here, it's actually going to be 3, 4, and 6. Because 2 is a smaller number, I'm going to count it in this fashion here. The E for ethyl comes first, so that's why the numbers might be out of order. For ethyl, in this case here, I have 2 similar methyl groups. I'm going to condense both numbers together. So 2, 5, and I'm going to use this word here, dimethyl. There's that prefix di coming back, but that di just means there's 2 somewhere in the picture. One of them is on 2 and one of them is on 5. Even if they both showed up on the same number, I would need to double it, like say 2, 2. It's totally possible that the numbers are totally out of order by the time you get to the IUPAC name. That's the group that defines all these naming rules for us, but the numbers are out of order. We already made sure that the numbers were tiny in counting that fashion. It's just because E came before the M for methyl. That's why the numbers are out of order. So be careful to practice a lot of this naming of chemistry here, especially as we got to different functional groups. We needed to change endings, and there's a lot of detail there. So first section of this one here is just a lot of organic nomenclature. Let's just let's just throw on some functional groups here so that we can actually get some practice. You do need to memorize the names of the functional groups. In general, they're just going to give you one functional group at a time, but I just want to give you some practice with naming here. In this case here, we recognize the OH functionality. That's going to give the molecule some polarity. It's going to give it some hydrogen bonding relationship. The double bond here would actually make it a alkene. Sometimes you will have sort of the combination of the two here. This would in chemistry be called an enol because it's a double bond and an alcohol. But then because we've seen alcohol groupings here, it's a lower priority grouping. You can also refer to this as a hydroxy group if you want. Careful, it's actually called a hydroxyl when it's bonded like this, but when we're doing the branch, it's going to be hydroxy. And I'm just going to number for any carbon chain that has the double bond here, the parent has to go through the double bond, even if it's the shorter chain, and the double bond, what's called, takes priority. So therefore, the number of that has to be the tiniest, not necessarily going to be 1, but it has to be the smallest number. So in this case here, it would have been 1, 2, 3, 4. My double bond stretches over from 1 over to 2. This one here, the ending is going to be but. I'm going to actually put a number just like where the branches would have needed numbers. In this case here, we're actually putting the number in front of the ene part because the double bond stretches from 1 over to 2. We also, in this case here, have on branch number 3, a hydroxy grouping. You're going to have the branches the way you normally name it. Some other prefixes and functional groups. Let's do a C double bond O, OH like that. Let's make it a little bit longer here. Let's add on a NH2 grouping and maybe a triple, no, not triple. Okay, so let's do this picture here. In this case here, we recognize the NH2 to be an amino grouping. It could also be, if this is the only functionality, it could be something amine as the parent ending. But in this case here, we actually have a carboxyl family. Carboxylic acid here will take priority. The carbon in the carboxyl group is carbon number 1, so you don't actually technically need to number that, but just making sure we're counting it properly here. This one here should be 4, amino, and then this would be pent for 5, because it's a carbon chain of 5, but because it is a carboxylic acid family, this is going to be pentanoic acid. You do not need pentane 1-oic acid because I know that carboxyl group here has to occur at the end. It got a little bit funny when we got to the amide family. For amide, the functionality is going to be on the same carbon. I have a C double bond O, and it would be simpler if I had just an NH2. But sometimes those ones here are also substituted. So I'm just going to do this as an example for you here. Normally they don't get as complicated as this. In this case here, for this family, because on the N group actually does have a lone pair here. That fills up its octet. Because the N group here has the methyl and the ethyl substituent, I'm actually going to say N-ethyl for alphabetization, N-ethyl, N-methyl. There's an ethyl and a methyl bonded to the N side of it. And then I'm going to name the other side of it, which is the longest carbon chain. This is the other attachment with just the 2 there. We're going to call it ethan. And then we just change the ending to ethanamide or ethanamide. Right, so just be careful when you're naming of amides. Might look a little bit fancy like that. There are other functional groups here you should be able to recognize and do some naming. I've given you a quick summary chart here. We've talked about alkanes, alkenes, alkynes. A phenyl ring is the special group that a benzene group has. A halide is with a halogen, amino or amine, alcohol. If an O comes with single bonds in between, so COC like that, it is a ether grouping. Careful, the name is very similar, but this one here is actually an ester. Ester here is COO. These two groups are the ones that come in between branches. Through a condensation reaction, we can actually pull 2 carbon centers together. And then we just saw here carboxyl family and amide family. Sorry, that's missing an NH2 or substituted N's there. And we missed 2 other groups here. The special group here is actually just called the carbonyl group. A carbonyl is a C11O. If it happens to be at the end of the chain, we just emphasize it's a CHO group. The rest of it's terminal. It's at the end. I don't need a number for that there. CHO is an aldehyde, whereas if it happens anywhere mid-chain, if it happens in a cyclic compound, we're actually in the ketone family instead. So make sure you know how to name those organic families there. That gives rise to a lot of different functionalities. There's another listing of them, all the functional groups, special groupings that they have, as well as the suffix ending there. So first little bit of this chapter here was just basic naming, and then we did a quick section on isomers. So isomers here. Isomers, basically the iso part means something is the same. We actually need to start organizing our isomers here. For all our isomers, we're going to have the same molecular formula. We're going to have the same numbers of C's and H's, but something is going to be different about their arrangement. Depending on what's different, we can have different type of isomerism. So in the first case here, we have first division, first branching here is called a structural isomer. This one here says they have different branching. They have different attachments. So in this case, I physically need to break up the compound. Let's say I take that butane that we had from earlier. Remember, you want to do this structural isomerism here really systematically so we don't miss anyone. Basically, what we're going to do is we're going to start chopping off, start from the longest chain, chop off the ending. Now pretend that we actually have a shorter chain. In this case here, it would be a pentane instead. And now imagine I have a methyl group to resubstitute on. You cannot put a carbon branch back on carbon number 1 or carbon number 3 because that would just extend the chain. In this case here, we can only put it on carbon number 2. In this case here, I had to break a bond and I had to reform a bond. That means chemical reactions have to happen for this to occur. But what we're going to see for structural isomers, in fact for all isomers, they're going to have different names. This first guy here would have been called N-butane, a straight chain of 4 carbons, whereas this one here is only a propane no matter how I count it. This one here is actually 2-methyl propane. And in this case here, because that carbon branch can only occur on position number 2, chemists are super lazy. If I can drop it and it's unambiguous, you can drop that 2 there. It's not wrong if you still have that number, but you're going to find in textbooks, trying to be elegant, they're going to drop off those numbers there. That separates one type of isomers. These ones here are physically different chains, so they're going to have different intermolecular forces. A long straight chain here will have stronger London forces. This one's sort of compacted in on itself, a little bit weaker London forces. We can separate another type of isomerism here called stereoisomers. Stereoisomers, something is different about their 3D structure. So different spatial arrangement. This one doesn't involve breaking of bonds. So what we're going to have here for stereoisomers, subcategory here, we can call them configurational isomers. Configurational isomers just means 3D twisting around a single bond. So for example, if I have, let's take that 2-methyl propane from earlier. If I started off like this, and then later on, because all these single bonds here twist no problem, if later on it ends up looking like this, that is a configurational isomer. It's a conformational isomer. Oh, sorry, I just mixed that name there. Sorry, this one here I meant to say here. This one here is a conformational isomer. So conformation, the conformer is basically just rotating around a single bond. So nothing has really happened. It can interconvert between these two, no problem. Whereas what I wanted to say here for configurational isomers, this is when I got into that cis trans, EZ. This is when a multiple bond here doesn't twist very well, and it actually does need to break bonds, just like in the structural case. So down the configuration isomer here, this one here, I would need to involve breaking pi bonds to actually get in between these structures here. For this one, especially and only for alkenes. For alkenes, because the double bond here doesn't twist, and because both carbons that are involved in the double bond, they hold 2 groups, I can have, let's say, A, B, C, D. We started off just by saying, well, let's say A is equal to C. If both carbons are holding the same group, and they happen to be pointing in the same direction, both of them are pointing up, based on how I drew it here, we call that the cis isomer. We saw that cis and trans was a little bit limited because it had to be the same. Instead, what we did is we defined the priority. The priority is basically based on the atomic number, priority by atomic number. And basically, the higher priority group, even though A may not be necessarily the same grouping as C, if this is the higher atomic number and this is the higher atomic number, if both of them are on the high side, we instead call it the E. That was from the German Entgegen. Entgegen means the same side. Cis also meant the same side. Usually cis is going to be E, but we saw a compound or two that actually differs from that. The other one there is if the high priority here, if I have the same carbon double bond, it could even be sort of mid-chain. If I have the high priority on the opposite ends of the double bond here, we call that, you used to call it the trans isomer because the groups are across from each other, and now we're going to switch over to Z, which is the Zusammen, which means that they're opposite sides. So we're going to prefer to use the EZ language because that's a little bit more generic than just cis and trans. They're trying to phase out that cis and trans language. In that case there, we are twisting around the pi bond. I need to break that sideways overlap or else I can't interconvert one to the other. Then your favorite one here is optical isomers. For optical isomers, as the name suggests, this is when we got our R and S sort of notation. This is only going to happen around a chiral carbon. A chiral carbon is a carbon that has 4 substituents. Because it has 4 different groups that I can recognize, there's actually going to be some orientation whether the groups are clockwise or counterclockwise. So in this case here, we're going to have a carbon. It's going to be substituted by 4. Try to draw it with the wedge in the dash notation. It could be in any orientation. Remember, the rules are to assign your priority. We're going to go carbon number 1, 2, 3, 4, depending on what your element atomic numbers are. If they're both the same number in the first attachment, you go to the next attachment. We're going to always point our 4 group away from us. That's the only time we start looking at clockwise, counterclockwise, and then looking at the 1, 2, 3. Hopefully you can be able to define this for me here. In this case here, because the 4 is already away from me, in this one here, it is twisting in the clockwise direction. Clockwise, we're going to use R as a notation. R means rectus, which means it goes clockwise. If I have a mirror image of this, the relationship here, we're not actually breaking any orientation. So let's say I have the carbon in the middle. I guess I should call this E, or else it looks like a carbon as well. So I can have a mirror image. I can have still the E group on the other side, a B, and a D group jumping out like this. It's going to turn out just like your left hand and right hand. In this case here, it does not superimpose together. The relationship between these two are called enantiomers. Enantiomers are opposite at every single chiral center. R has switched over to the sinister. Sinister here is a counterclockwise orientation. These ones here are optically active, so if I put plain polarized light, basically I send in light that's sort of in a certain orientation. As it interacts with something that's R or S, it's actually going to twist that orientation as it goes through the sample. If I look at it down the barrel here, I look at the orientation, the light should have came in this way, and I actually look at how far bent it's over. The R will bend it one way, while the S will bend it the other way. It's possibly that I'm not optically active if I have, it doesn't just have to be I'm not R or S, it could be what's called a racemic mixture. A racemic mixture or a racemate, mixture. Sorry, I think it's either. Racemic mixture here is a 50-50 mix of R and Fs. So R wants to twist it one way, S wants to twist it the other way, and therefore there's no overall optical activity. In chemistry, they want to be really careful with optical chemistry. Sometimes chemicals are more active when they're R or they're S, and we had a sad case here in pharmaceutical chemistry. In the one case, it was a good pharmaceutical, a good drug to treat a condition. On the other one, it caused a lot of different defects and destruction for the body. So be really careful with the chemistry, R or S. Just before we leave this isomerism here, we have 2 last features. One is what's called a diastereomer. A lot of us, for biochemistry, especially when you looked at like glucose, they actually have many different chiral centers. Hopefully you did these as Fisher projections here. Because I may have multiple chiral centers, that means each of the chiral centers may either be R or S in some orientation. A perfect enantiomer will actually be opposite at every single position. So if I have a perfect enantiomer, it would be that one's R, so S, S, R, and R. That's an enantiomer, but what if we were only different in one of the positions? So what if our structure here, most of them were the same? What if we were still R, S, S, but only one of them have flipped? Sure, that part there has become the mirror image, but because the rest of them have not become mirror images, in this case here, these are referred to as diastereomers. Diastereomers are mirrored at some centers, but not all of them, like an enantiomer is. The other one here for cis-trans here, cis-trans I was saying does occur for double bond as well. Cis-trans also occurs for a ring as well. So if I have a ring, Basically, it's floppy. If I have a 3-carbon ring, it's super unstable. That's going to break apart really quickly. But in this case here, if I also have a high priority group here and my high priority groups are opposite, you can still refer to this as a trans-isomer as well. So in that case there, that's just isomerism in general here. Let's switch over to review some chemical reactivities. This is when the organic chemistry got fun. This is when we actually needed to do that mind map here. Let's see if we can just do a quick overview of the reactivities. Starting off with our family of alkanes. Alkanes in general are very boring. They only behave in 2 types of reactions. An alkane, you can just burn them. You can react it with oxygen. Alkanes burn really well, assuming that there's enough oxygen. They're going to produce CO2 and water. Later on, we're just going to summarize them as combustion products, because especially if these are substitute alkanes, if they contain sulfurs and nitrogens, I'm going to get some SOx and NOx. That would be different combustion products as well, but generally we just assume complete combustion. We found that under UV light, alkanes here, because they're single bonded here, single bonds are fairly strong and there's no really rich electron dense regions that can actually attack. We found that under UV light, that was specific here for an alkane bond, for UV bond, it can actually substitute it with chloros or bromo groups. That's actually one way to actually recognize an alkane. We're going to use bromine. They call it bromine liquid. Bromine is actually a brownish color. Basically, if you shine UV light on it, we're going to see that the brown color substitutes into the compound. I may end up with something like this, so maybe a mono-substituted ethane here. And in that case, I would lose brown color because bromine is no longer in its diatomic form. If I'm in the dark or if I have not UV presence, the reddish liquid will stay. So if the red color disappears in UV, I know it's the presence of just alkane single bonds. If it stays, that means there's no reaction just yet. So UV, careful, you can do this. This one is called the free radical chain mechanism. So radical chain mechanism. You do need to be able to separate these categories here. Basically what happens is, let's take our chloro as an example. First thing is our initiation step. That's our starting step. Initiation, this is why we need UV. You can just pulse UV light. Basically, you want to form some chloride radicals. This is chlorine with an unpaired electron, not charged, but this unpaired electron is super unstable. And because of this, this chloride radical is going to end up attacking your alkane. And what's going to happen here is this chloride is going to start picking off some of these bonds here. Let's say in the past, I had a CH bond like this. I'm going to do a fishhook. I'm going to do just a half arrow. The half arrow implies that it's just one electron that's attacking. One electron goes back to the carbon. After that step, this is all called the propagation step. This is how it sort of repeats after. Most of the alkane was perfectly fine. The alkane has now become an alkyl radical as well. And then we have formed an HCl. So chlorine is now happy, but that chloride radical here, if I have other Cl radicals that end up attacking, notice when I draw these arrows here, I draw it, don't just draw, oh, this guy attacks this guy. We're actually drawing from the electrons where it starts to where it ends. In this case here, this chloride attacks it, and overall I end up, that's actually a termination step. That's actually an ending step. But it turns out if chloride was actually a diatomic here, that actually just regenerates the chloride radical. I'll show you this here. So chloride, let's say this right here is reattached to chloride. It's possible that this chloride here actually was diatomic like that. So when that fishhook goes here, that one goes over here as well. That's going to regenerate another chloride radical, and the chloride radical is ready to attack another position somewhere on the alkane. So what ends up happening is over time, we end up having this propagation. We call it a chain reaction because it sort of cycles in on itself here. Make sure you can do those steps there. You will get trace amounts because we do get this radical here. It's possible 2 of these get together. So it's possible I may have that sort of orientation. Maybe this one here fishhooks with this one here. It's possible we get trace amounts of a longer alkane. This is not the best way of actually forming a longer chain, but we do get trace amounts, very limited amounts of that one there. So in general, alkanes in just overall are really boring. We switch over to alkenes, which are a lot more interesting. The alkenes, the reactive site is the double bond. When you define an alkene, don't just say double bond. Say a double bond between carbons. I could have had double bond between oxygens. That's not an alkene. An alkene here has an electron-rich region. Because this is an electron-rich region, you can refer to this part here as the nucleophile. What's going to happen here is we're going to have other compounds come around it, and what's going to happen is we're going to try to let this electron-rich region actually attack other areas. So we're going to start off here. Let's summarize some of the structures. let's add just a plain old hydrogen to it. In this case here, because this region here is electron rich, I can show you the mechanism for this right here. The electron rich region, this time it's going to be a double-headed arrow because both electrons are going to attack the hydrogen. In this case here, both electrons will go back to the other hydrogen here, sort of a middle step here. I'm going to have C, its double bond is now going to become more saturated. I'm now going to pick up that one extra hydrogen. It's going to have that one extra valence sorry, that's a positive charge here. And then we're going to have a H with a negative charge, and the H, now that it has that lone pair, with donating a lone pair, that actually makes it a Lewis base as well. That's our, in this case here, it's our sorry, that's our nucleophile here. It's actually attacking our electron-rich place here. And basically what's going to end up happening is we're going to have C, and then we're going to have added hydrogen across the double bond. We call that process there hydrogenation. So hydrogenation, I'm adding a hydrogen to the entire molecule. This is much more interesting when we actually add a halide, especially when it's asymmetrical. So let's take any old alkene again, but let's add it to a HX. So some halogen group. Basically the same reaction happens. The double bond is going to pick off the hydrogen. We have something called Markovnikov's rule, just for a hint for ourselves. In this case here, basically what ends up happening is we want to form the more stable carbocation. Markovnikov says when we add an asymmetric alkyl halide here, the hydrogen adds to the side that already has more carbons. If you remember the reason for that here, well, carbon here, the one that was already more hydrogen substituted, if I end up picking off that hydrogen, I end up forming a carbocation that is, because of that inductive effect, stabilized. In this case here, it's called a secondary carbon because it's actually bonded to two other carbon neighbors. There's actually a little bit of electron donating effect because of this extra carbon attachments. It's actually going to help stabilize that carbon center for me. And based on that, it stabilizes this carbocation intermediate, and the X likewise can attach there. So we had Markovnikov, and then we're going to get this one here as our major product. Yet again, we're going to have a double bond have now formed a single bond, and we've now formed an alkyl halide. You can also call it a halogen alkane. It can attack a XX as well. I can add a halide to both of them, but definitely follow Markovnikov, especially when it's asymmetric. Alkenes can react itself to become polymers of itself. So polymer reactions, basically I have alkenes. Basically I try to draw these structures. Let's say I have a methyl group on these ends here. The double bond here starts attacking the next one along the chain, the next one along the chain. It's going to end up forming a multiple repeating pattern where the double bond has still become a single bond, but again we're going to have just a repeating unit to the nth, and therefore we get a polymer. It's basically this one having added to itself many times. So we call those their addition polymers. Then we get into families like alcohols. For alcohols, how do we make an alcohol? We can actually take an alkene, C double bond like that. Basically what I want to substitute is a water molecule as represented by HO. Unfortunately this one here has to be catalyzed by a concentrated sulfuric acid. Basically the acid group adds first, but overall we're going to end up with C single bond. You will need to memorize some of these reaction conditions. So this one will be H and the OH, and suddenly we have an alcohol. Alcohols are sort of the least oxidized form of them. In this case here, we have what's called a primary alcohol. If the other ones here are a hydrogen here, if we're a primary alcohol, we can actually oxidize it. You don't need to know the mechanism for this one, but you're just going to add a oxidizing agent. So in general, we just say plus O. Some oxidizing agents we've seen is you can add KMNO4. That's one example. That one we try to avoid because it's a really strong oxidizing agent. It tends to oxidize other functionalities as well. So we use the more stable one here, acidified dichromate, Cr2O7, maybe a little bit heat as well. In this case here, if you oxidize it a little bit, if you do distillation, you can sort of catch it midway. By catching it midway through a distillation, it ends up forming the aldehyde grouping. So C single bond C like that, double bond O. You see that we're more oxygenated, we've lost the hydrogen. Distillation will give you that middle step. If we just let this continue to reflux, continue to vaporize here, we're going to actually end up getting the fully oxidized form, which is with the carboxylic acid, fully oxygenated here. In that case there, we'd use the terminology reflux. That's the oxidation process here. For a reduction process, while I have it on the screen, for reduction, you also had two conditions. Going back the other way, you can actually bring an aldehyde back to an alcohol just with a more stable reducing agent like sodium borohydride, so NaBH4. That also has to be in heat as well, so that's going to be reducing there. This one here is a weak oxidizing agent. It's a weak thing that reduces. So therefore, if I want to reduce from a carboxylic acid back to an alcohol, I actually need to use something stronger. Both of them use the hydride to actually do the reduction for it. But in this case here, 2 steps, so make sure you do say step 1, step 2. Step 1 is actually a heat treatment with lithium, aluminum tetrahydride here. This one here has to be in a dry ether, so it can't be in a polar molecule, and we actually reacted with some acid afterwards to pick off the other groups, and then it doesn't stop in the middle step, it actually completely goes back to that first primary alcohol kind of step. Secondary, so if I have a secondary one, when I fully oxidize, this one here just forms a ketone. I can't actually get to a carboxylic acid because I would have to break the carbon structure. A tertiary here would have no reaction. Lastly here is, let's take a look at our alkyl halides. This is when we had our substitution sort of reactions. So if I have an alkyl halide, carbon, let's say hydrogen, hydrogen, and maybe I have some halogen group, so maybe an X group. Essentially what's going to happen is, because of the polarity of this bond here, there's going to be a partial positive on the side, a partial negative on the side here, and if I have something that's willing to actually attack it, in this case here we'll do nucleophilic substitution, we're going to have something that is very electron rich. Say I have a NH3 grouping, it has that lone pair. What we're going to have is this one here is going to be called the nucleophile because it's already electron rich. This nucleophile is going to attack the carbon. The bond is just going to go over the other side here. We saw 2 separate mechanisms for this. This one here could have been an SN1 mechanism or SN2 mechanism. In the SN1 mechanism, basically the first step actually forms the trigonoplanar just sort of intermediate here. This one here is already formed, and basically if that's the case, we're going to have the ammonia be able to attack from either the left side or the right side. We're going to get a racemic mixture. We might get flipping of the orientation, maybe not. Whereas in the SN2, the 2 actually stands for bimolecular. It stands for the fact that the rate law actually does depend on both the halide, so let's just say CX, as well as the halogen group. In this case here, I'm doing NH3. Bimolecular, it's rate order 2, but this actually all takes place all at once. So you can imagine having a transition state. So this one here was a carbocation intermediate. This one here can be actually isolated, while a transition state just happens to be in the process of breaking forming bonds. We actually get a 5-carbon transition state, a hydrogen, hydrogen, hydrogen. And in this case here, because of how this thing here is happening all and concerted all at once, what's going to happen is, as the amine itself attaches, as it forms that new bond, it's going to push off the X group. And eventually, especially for an SN2 mechanism, we're going to have, yes, finally substituted NH3, we have a CH, H, it's going to actually have flipped the orientation. We have H, H, and H like that, right? So definitely there's an inversion of stereochemistry, inversion of stereo, while the other one could have made, attack from both sides, could have made an RS, especially if it's chiral. So that one there, SN1, SN2, we talked about when it's favored. So SN1, because we formed this one here, for an SN1 reaction, we want to preference a tertiary carbocation because we're going to have high inductive effects, positive inductive effects. And also, tertiary makes it hard for SN2 to do this concerted reaction because this has to take place all at once. If I have very bulky side chains, it's a little bit hard to actually attack. So in this case, SN2 actually relies on primary, and primary here will actually be, because I have not bulky substituents, a little bit easier to attack. And similarly here, primary here has less inductive effects, but we're going to have better steric effects. Steric has to do with sort of the orientation of the attack, and we'll go from there. Okay, so that's how we actually make an amine. We can actually add a CN group, a nitrile in exactly the same cyano group to form a nitrile. And then we actually had some condensation reactions. Fortunately, in the new curriculum, we don't need to know it in too much detail. Basically, what's going to happen for a condensation, as the name suggests, we're pulling off a small group, and we're going to end up gluing two molecules together. So if I take that amine group that I just formed, so an amine of some sort, I react it with the alcohol family. So in this case here, actually let's do amine. Let's actually do carboxylic acid first. So carboxylic acid, the amine would actually form an amide here. This one here we demoed in class, a little bit of heat treatment, a little bit of sulfuric acid. The carboxylic acid group would come with a Cu like this. An alcohol group would be an ROH. Sometimes I use R as just a general group. And basically what ends up happening is when I end up pulling off, I'm going to condense off the H2O. I'm going to remove the H2O, and I'm going to have glued that carboxylic acid part here, C double bond OO. I'm going to have glued the R group on top, and now I've formed an ester functionality. So that forms an ester in a very similar fashion. If instead of adding the alcohol, if instead of the carboxylic acid group is added to a amine group instead, and again, another heat treatment here, we're going to end up with amide as a structure. Right? So hopefully you can practice for yourself just drawing that mind map, see if you can do these interconversions. We can sort of make from one thing go to the other thing here. One thing I forgot to mention is trying to recognize different functionalities aside from different reactivities, especially between, let's say, alkanes and alkenes. One way I already mentioned was using that bromine liquid. The other way is because this burning here, complete combustion for an alkane, is a lot cleaner, we tend to get a very clean burn for a alkane, while as the carbon to hydrogen ratio actually goes upwards, alkenes and alkynes, these ones here typically have more incomplete combustion, and in that case there we tend to get a dirtier, more smoky flame. So just watch out for that there. Last reaction, just hang in there here. We're going to have a benzene structure. Benzene, although it does have that aromatic ring, it doesn't behave like any other alkene because of that resonance stability. Even we did models with having one double bond, two or three double bonds here. It has that resonance stability. It really doesn't want to lose the stability if it can. So in this case here, instead of doing a addition reaction, like adding something across a double bond, benzene actually does something called electrophilic substitution. And this one here didn't really fit on our mind map because benzene is sort of strange by itself, but you definitely do want to know at least this reaction here. Say I have a benzene. Benzene looks like a turtle. Right? This is just a resonance form. It's actually not double, single, double, single. These double bonds are actually delocalized. They're shared by all the carbon centers here. The one reaction that we did is we started with reacting it with a nitrating mixture. A nitrating mixture is HNO3 and H2SO4. You can look at the mechanism for that one there. This one can happen at about room temperature here. This nitrating mixture, in the mechanism, we produce the really reactive nitronium ion. Nitronium one is NO2+, and we end up basically adding that NO2, super reactive there. We actually add the NO2 across, and we have a H+ afterwards. And then what we're going to do is we're going to reduce this back down here. We're going to use tin as our catalyst, concentrated HCl, heat under reflux, and we basically reform our ring. Benzene can relax a little bit here. It sort of lost the ring for a little bit somewhere mid reaction here, but eventually it reforms it. Now we've reduced it to a sort of NH3+ group, and then by reacting it with the hydroxide, I end up getting just the phenyl group back. So make sure you know that mechanism. That's the only example of an electrophilic substitution. The other reactions that we've done, just alkyl halide. This was nucleophilic substitution, and I should have mentioned these earlier. Alkenes, this one here was electrophilic addition. Right. We didn't do nucleophilic addition, so if you continue in organic chemistry, you'll see an example of that. All right, so sorry for the long lesson, but hopefully that's a nice recap for you. Do look in your notes for some of the details I may have glossed over, but hopefully that'll help you with your study. Thanks, guys. Take care.